Imagine this tiny particle, right? And it's absolutely booking it in one of those super fast circular accelerators.
Near light speed already.
Exactly. But then think about this. It's also moving because the Earth spins and the Earth orbits the sun.
And the sun itself is whizzing through the galaxy.
And the whole Milky Way is hurtling through space. I mean, it feels like all those massive speeds should just, stack up.
Yeah, add together.
Could it actually break the speed of light? It kind of feels like it could, doesn't it?
It really does. Our everyday intuition just screams, add 'em up. But that's what we're diving into today, why Einstein's special relativity basically says, nope.
A universal speed limit.
Precisely. There's a fundamental reason why nothing with mass can hit or exceed that limit. And it all comes down to the speed of light itself, specifically in a vacuum. It's constant.
Constant no matter what. Got it. And, in normal life, adding speeds is dead simple. Like, you're on a train, maybe going 50 miles per hour. You toss a ball forward at 20 miles per hour.
Yep.
Someone's standing still watching. They see the ball moving at, 70 miles per hour. 50 plus 20. Easy.
And that simple addition, that's what physicists call Galilean relativity, or classical velocity addition. Works like a charm for trains and balls and, well, anything not going ridiculously fast.
Okay, but that's the catch, right? Ridiculously fast.
That's exactly where things get weird. And honestly, really interesting. When you start pushing speeds up towards the speed of light, that simple adding rule, it just breaks down.
It doesn't work anymore.
It doesn't. And that's where Einstein's special relativity comes in. It gives us the correct way to think about how space, time, and velocity work together at those extremes.
So you can't just add up the particle speed in the accelerator plus the Earth's speed plus the sun's speed and all that cosmic motion.
Nope. There's a different calculation involved. Special relativity provides a specific formula for combining velocities when things get, relativistic.
A formula designed to respect that speed limit.
Exactly. It ensures that no matter what speeds you're combining, the result never actually reaches or surpasses the speed of light, c.
All right, I think we need to see this formula. Lay it on us.
Okay. So for things moving in the same direction, the relativistic velocity addition formula looks like this. V equals fraction time. V1 plus V2 on top.
Okay, V1 plus V2.
Divided by 1 plus another little fraction.
Okay.
V1 times V2 divided by C squared. So V1 plus V2, 1 plus V1, V2,
Okay.
C2.
Okay, let's break that down. V is the final speed we want, the combined velocity.
Correct.
V1, that's the particle speed relative to the machine it's in, the accelerator.
Yep.
And V2 is the speed of the whole accelerator set up moving through space because of, Earth spinning, orbiting, all that stuff.
Right, all that background cosmic motion bundled into V2.
And C is the speed of light.
Okay. Now the really crucial part, the magic, if you like, is in the denominator, that bottom part. 1 plus V1, V2, C2.
What about it?
Well, think about it. If V1 and V2 are small compared to C, like everyday speeds, then V1 times V2 is tiny, and divided by C squared, it's practically 0.
So the denominator is basically just 1.
Exactly. And then the formula just becomes V1 plus V2, 1, which is just V1 plus V2, our simple everyday addition.
Okay, that makes sense. But when speeds get huge...
Right. As V1 or V2 or both get closer to C, that V1, V2 term becomes significant. And when you divide it by C squared, it's no longer close to 0. It's a real number.
So that whole term, V1, V2, C2, it adds to the 1.
Precisely. Meaning the denominator, 1 plus V1, V2, C2, becomes greater than 1.
And if you divide the top part, V1 plus V2, by a number bigger than 1.
The result, V, has to be less than just V1 plus V2. And mathematically, it works out so that V will always be less than C.
So even our superfast particle, let's say it's doing 0.999 C inside the accelerator.
Not really pushing it.
And the accelerator itself is moving at, I don't know, some crazy fraction of C because of the galaxy's motion. When you plug those into that formula, the relativistic one, the final answer, V, will still be less than C, maybe 0.9999 something C, but never actually C.
That's it, exactly. It gets incredibly close, asymptotically close, you could say, but it never crosses that line. It's like the universe has this fundamental speed governor built into the fabric of space-time.
Wow. So it's not just a theory, it's how space and time actually bend or behave.
It's how they behave. It's a core feature of reality at high speeds. Any observer, no matter how they're moving, will always measure that particle's speed to be less than c. The laws of physics themselves uphold this limit.
Okay, so summing up then, all those cosmic speeds, Earth spinning, sun orbiting, galaxy moving, they're real, They add something to the particle's motion.
Absolutely.
But they don't just stack up simply like adding miles per hour on a highway when you're near light speed. This relativistic addition thing kicks in.
It does. It ensures nothing with mass ever hits C. End of story.
It really puts that speed limit in perspective.
It does, doesn't it? And it leaves us with a pretty profound question to chew on, really.
What's that?
Well, if the speed of light is absolute, if everyone measures it as the same regardless of their own motion, what does that force us to conclude about things like distance and time? If speed, which is distance over time, is constant, but velocities add relativistically, what gives? What has to change?
So time and distance themselves must become relative, depending on how fast you're moving.
Exactly. That's the next layer of this relativistic rabbit hole. Something to ponder how our fundamental notions of space-time have to warp to keep the speed of light constant for everyone. It's truly mind-bending stuff.